Let's talk about thermodynamics. We touched on thermodynamics. I think it was in the first semester when we did things with calorimetry. Or was that this semester? Last semester, yeah. So that was just exercising how to measure heat transfers. The discussion in chapter 17 is what effect, how do we explain some chemical reactions that, actually all chemical reactions, how do we explain all chemical reactions, regardless of whether they evolve heat, absorb heat, or do neither? So that's where we're headed. Remember when we did kinetics, we had our description of the reaction, which was progressing from left to right. And then we have energy here. So if we have energy of the reactants, say, was here, and the energy of the products was, say, down here, then we had to go through a transition stage right here. And this would be something like an activated complex. Or our collision theory, when a reaction occurs, you've got to have an impact. One reactant, at least one reactant, has to impact with the other, or it's a little more difficult to explain single reactants, but I suppose they would smack into each other, smack into your neighbor. But anyway, you need a certain amount of energy, right, between here and here, the activation energy, to make that reaction go. So if we divide this diagram into parts and just draw a line right here, then everything over here, these two sides, are discussing topics of equilibrium. And in particular, this is where thermodynamics comes in. So the discussion of thermodynamics is essentially a state function, because it only is interested in what happened, where'd you start, where'd you end up. Whatever happens in the middle doesn't matter. And then, of course, in here was our discussion of kinetics. Right, how fast does a reaction go? And that means that kinetics is a path function. It depends on the path that the reaction takes as to whether it will go fast or slow. So when we introduce a catalyst, right, we're actually creating a different path that allows it to go faster, because the new path doesn't take as much energy. But when we were talking about the outer boundaries, the reactants and products, we're talking about state functions. And that's where we are with thermodynamics. This is a state function. All right, well, I'll leave that there for now. Okay. One thing that thermodynamics does allow us to do is to predict whether or not a reaction is spontaneous, either in the forward direction or the reverse direction. If it's spontaneous to the right, it'll be non-spontaneous to the left, and vice versa. If it's not spontaneous this way, just flip it around and it'll be spontaneous the other way. And that spontaneous means exactly what you think it does. Spontaneous means no outside intervention required. You put the reactants together and they go to town. Now, they may go to town slowly, like diamond in an oxygen atmosphere, thermodynamically speaking, is unstable and it ought to degrade. right? Eventually produce all carbon dioxide. It's just that it takes a million years to happen. But thermodynamically, the reaction, the oxidation of diamond, the carbon in diamond is favorable. It's spontaneous reaction. All right. So let's look at the problem of predicting whether a reaction is spontaneous based upon this scenario. We have a gas contained in a 4-liter bulb at a temperature of 32 degrees. So we got this bulb at 32 degrees C, and it's 4-liter volume, and there are 2.4 moles of gas in it. Okay. It's connected to it by a valve to another bulb. And they don't tell us what that is because it doesn't matter. This one is a vacuum. Now, this, strictly speaking, is not a chemical reaction, but it's trying to lead us in that direction. Oh, they do tell us it's 20 liters. Okay. And the temperature is constant, right? So whatever happens, the temperature is 32 degrees throughout the process. What will happen when we open that valve? Right? Intuition tells you it's all headed for the vacuum until it's equalized. Right? In our study of gas laws, we learned how to calculate. Right? We could calculate the final pressure in here. So when we open the valve, we get the gas swishes over there. What's the driving force? Right? Because the temperature is constant. There's no change in energy. It's just a change in volume. Got the same number of moles. We know the laws tell us, gas laws tell us what will happen. But what they don't tell us is why it happens. All right, so we've got some definitions here, some terms to deal with. Let me see where it's going. Okay, I'm gonna leave that scenario there because we're gonna use it again in another slide. Remember enthalpy, like the potential heat evolved or absorbed by a reaction? That's what delta H is. Delta H is enthalpy. But to carry it further, we need an expression of what's internal energy. And when we say internal energy, we're referencing a system. I described this before, didn't it? The way we approach system analysis is there's the system and everything else is surroundings. And usually what we do to simplify things and make it more manageable is we isolate the surroundings so that now we're dealing with this much surroundings and this much system. And whenever we talk about any type of matter or energy transfer, the sign matters. So if heat transfers in, that's a positive value because it's relative to the system. If heat transfers out, Q is negative. And we can apply the same logic to these values. If enthalpy changes if it's negative, that means it's exothermic. The heat's leaving the system. And positive, it's endothermic. Internal energy means all the energy for the system, everything included, kinetic potential, whatever you can get your hands on. That's the total. And the enthalpy then is equal to the internal energy plus this value, which references gases, right? It wouldn't have any meaning for liquids or solids. So we're talking about a gas here. So any change in pressure and volume, or if you have a constant pressure and the volume changes, that affects the expression of internal energy in enthalpy. Heat flow is Q. We did that one already. Q is heat flow, and W is work. We define work yet? Work is force times the distance. That's from physics. So if you apply a force through a certain distance, that's work. Okay. So if I, let's see, if I stand here and push on this wall, I'm applying a force to the wall, but is it moving? No, I'm not doing any work. I'm expending energy, but there's no work being done. So where's that energy going? Because you can't create energy. You can't destroy energy. Where's all that energy going that I just expended pushing on the wall? Turns into heat. Yep. Or friction, heat. It's got to go someplace. And that's as good a place as any. Okay, so we've got these four terms to deal with. Enthalpy, internal energy, heat, and work. So if we try to calculate the values here for this system that we just described, we find that all of them are equal to 0. Right? There's been no heat transfer. Why? Because the temperature is constant. You can't transfer heat with a constant temperature. The internal energy is the same because it's within the system, right? This is part of the system. So the whole system still has the same energy as it did before. When we say pressure times a change in volume, change in volume and pressure, that depends on a movement relative to the surroundings. And nothing has happened relative to the surroundings here, right? This is the surroundings here. This is the system. Everything is internal to the system. So we haven't done any changing to the pressure and volume relative to the surroundings. If we change the volume here, that means this thing would have to expand or contract. And it's not, it doesn't do that. So we haven't changed that at all. And that means if this is 0, that's 0. There's been no change in internal energy. There's been no change in heat, right? No exchange there. No work was done because the gas was expanding. Was it pushing against something? No. Right? So all of those are 0. Right. Why did we go down that rabbit hole? So what's the driving force for the process? Why does it do that? Right? If there's no impetus for the expansion of that gas into this vacuum, why does it do it? We need a scapegoat, right? Something to blame for the movement of that gas. What's the driving force? And a lot of big minds, big brains, spend a lot of worrisome hours trying to figure this one out. And they came up with this word, a new term called entropy. Entropy is the reason. Now, in simplistic terms, Clausius proposed entropy in the beginning, but there were a lot of people working in that area, so they picked up on it pretty quick and ran with it. And this was at the end of the Civil War when Clausius proposed that. Of course, he wasn't over here. He was in Europe. There he is. My goodness, he looks like those eyes could cut through steel. He's not a happy person. I think pictures taken during that time period, they all look that way. I think the photographers told them to look that way.
Are they photographers or are they the names?
I think that's a photograph. 1865. Yeah, they had photographs. Yeah. And they had the the photographic plates were so slow that you had to be real still for like 5-10 seconds. Okay, so here's our expanding gas into an evacuated bulb. And what's the difference between the images? The red dots are representative of the moles of gas. So we got the same number of moles of gas in the top one and the bottom one. But now, in the bottom one, the moles of gas have more room to bounce around. Okay, that's the key. They have more space. That's an increase in entropy. Now, the simplistic description of entropy is centers on the word disorder. Right? That's not entirely wrong, but a rigorous explanation of entropy has to go beyond a disorder. Like there's more entropy in my office than there is in this room. I mean, I got papers and stuff everywhere, just a mess. My son's room is like that too. There's lots of entropy in his room, disorder. An ordered situation is considered low entropy. And I'll refine that definition in a minute, but that's a good place to start to try to get a handle on what entropy is. So when a spontaneous process occurs, we can be fairly certain that the entropy of that system has increased. And we give it, entropy is S, but we always measure a change in entropy. Actually, we don't measure entropy, we calculate entropy. It's not a measurable variable. We have to know other things that go into the calculation and give us entropy. So if entropy is greater than 0, there's an increase in disorder. If it's less than 0, there's a decrease in disorder. And randomness is also another term that enters into the discussion. That's true. It's grossly oversimplified, but it's a starting place. So what entropy actually does is it's a statistical approach to the number of possible arrangements that are available to the system. We call them microstates. The more microstates you have in the product than you do in the reactant, the more likely you are to move toward products. An increase in the number of microstates will favor the spontaneous direction from left to right in the way we write equations. So here we have this came out of my textbook, I think, where we have different arrangements that are possible for 4 molecules divided between 2 bulbs. Right? It's possible to have A, B, C, and D all in one side. Right? That's 1 microstate. How many microstates can you have 3 in one side and 1 in the other? Right? Well, there are 4 of them, so you can have 3 in one, 1 in the other, and you can rotate around all 4 of them. So you can have 4 microstates with 3 on one side and 1 on the other. If you have 2 on one side and 2 on the other, statistical probabilities tell you that you can have 6 microstates. Okay? And you see A, B, and C, D, the first one. AB over here, CD over there, then you can have BC and AD, and you just go down the line, and you can have 6 of them. You can have 3 on the right-hand side and 1 on the left-hand side, which is the mirror image of Roman numeral 2. You can have 4 of those microstates. And then, of course, you can have fall 4 on the right-hand side instead of on the left-hand side, and that's only 1. So the most probable arrangement is the one with the most number of microstates, which would be Roman numeral 3. Right? Usually have 2 on one side and 2 on the other. Okay. We can speak of entropy in a couple of ways. One, the first one is the easiest to understand, is positional entropy. And what we're talking about there is the disorder of the material relative to its physical state. Solids tend to have a regular arrangement of molecules in their substance. That means they're locked in position. They have very few microstates available to them, but they're locked in position and they're more ordered as a result. So the entropy of a solid should be less than the same substance in its liquid state, because now the liquid state is has the opportunity for the molecules to slide past one another. So now we've created more disorder. And if you go to the gas, you've increased the disorder factor, the entropy, enormously. You've got the molecules are moving faster, they're farther apart, and they occupy more space. So their entropy is huge compared to the liquid and the gas, the liquid and the solid. That's a positional probability of those states. There are very few probable states for the solid to occupy. There are a few more for the liquid and many more for the gas. So that means the entropy of the gas is going to be much higher than it is than the liquid, which is higher than the solid. Then we can speak in terms of energy entropy. And this is not, I put a note there, it's not covered in the textbook, but I'm going to introduce it anyway. So if we consider the total randomness of the system and its surroundings all together, which use your imagination, we can either allow energy to leave the system or energy can be added to the system. If energy leaves the system, we're implying an increase in energy randomness to the surroundings. So the surrounding entropy increases and the system entropy decreases based upon the energy only. That's for an exothermic process. For an endothermic process, energy is leaving the surroundings and entering the system, which increases the energy entropy for the system and decreases it for the surroundings. Let's see, is there more coming? Yeah, there's more coming. You don't have to know this stuff. This is just an interesting fact. It picks up where I said this value cannot be measured. It has to be calculated. And it's based originally on Boltzmann's equations, right? Entropy is some proportionality constant K times the natural log of W, which is the number of possible microstates. That doesn't mean work. Little w is work. His W is the number of possible microstates available to the system. And they can be huge. Right? Just trying to calculate based upon that equation, I think is impossibility. So we need other equations derived from that. And we'll get there. So let's see if we can, based upon what we know so far, if we can predict the change in the sign of delta S for each one of these processes. And I think we should confine our interest to the system. So when we evaporate alcohol, we got liquid alcohol goes to gas. So delta S should be positive, correct? Yeah. Come on. Oh, there it is. Freezing water, it's going from liquid to solid. The entropy should decrease. It's becoming more ordered. Compress an ideal gas at constant temperature. You're constricting it into a smaller volume, which means its entropy has to decrease. It has less volume, so fewer microstates are now available to it. If you heat an ideal gas at constant pressure, and it doesn't say anything about the volume, but if you add energy to it, this is energy entropy. If you add energy to the ideal gas, then you're going to have more energy entropy, so it should increase. Yep. What about dissolving sodium chloride in water? It starts as a solid, right? You add those little cubes. Right? We looked at them, didn't we, under magnifying glass? Throw them in the water, what happens to them? They break apart into ions. Now they have more microstates than they did before. So entropy should increase for dissolving. Actually, sodium chloride or any solid you dissolve in water would increase its entropy. All right. The laws of thermodynamics. Right. First law, it has to do with energy. The change in energy for the entire universe is zero. The universe has all the energy it started with and all the energy it's going to end with. For the whole universe, there's no change in total energy. Now, you can get changes in energy on a localized level, right? If we isolate a system and surroundings, you can get changes in energy. But for the whole universe, it's zero. Second law of thermodynamics. Says that in any spontaneous process, there's always an increase in entropy. So that is, for spontaneous processes, the process is spontaneous. And at this point, we're lumping physical and chemical processes, any process. Spontaneous, the change in entropy is always zero for the universe. Okay, that's the universe. And like I said before, if we isolate a system and surroundings, you can get negative values of delta S within that system and surroundings. Here we go. Yeah, I just said that. So overall, the universe is becoming more disordered, right? It's running down, as they say. You may have heard that in popular entertainment. All right, I already gave you that one. All right, so what that means is we can also express it in this way. The entropy of the universe is equal to change in energy for the system plus the change in entropy for the system and plus the change in entropy for the surroundings. Right, so if delta S for the universe is always greater than zero, then the balance here determines whether it's which one is negative and which one's positive. Right? We could get this one positive and that one negative, but the difference, the sum, would have to be positive for the whole universe. Okay, I like this one better because we rarely ever discuss thermodynamics in terms of the whole universe. That's our starting place. But when as a practical matter, we have to isolate our system and surroundings so that we can study them. So if we say, instead of universe, we say just total. The total entropy is the sum of the system and the surroundings. And I'm not sure about your textbook. I haven't looked at it in a little while. Some textbooks will say delta S universe when they actually mean total. I know my textbook does that. So that's probably why I made this distinction. All right. So if we use this one with total and delta S total is positive, if this is a positive value after we add those two together, then we know this is a spontaneous process. If it's negative, then it's spontaneous in the other direction. It's non-spontaneous in the forward direction, spontaneous in the reverse direction. Am I missing some slides? Okay.
I was making sure I was.
Okay. And of course, if delta S is 0, we're in a situation of equilibrium. There's no impetus for the process to go either direction. All right. Let's say we have a process that's, this substance is going from a liquid to a solid. Which direction involves an increase in energy randomness and which one involves positional randomness? Well, if we go from a liquid to a solid, we know that we have to give up energy, right? So then increase in energy randomness would be from right to left under this situation. Decreasing from liquid to solid. The process is exothermic, right? So if we lose energy, that means from left to right, energy randomness decreasing from liquid to solid. But it asks us for increase. Increase in energy randomness will go the other direction, solid to liquid. Okay, I'll agree with that. Positional randomness, on the other hand, increases from right to left. Well, both of them do. Yeah, both of them. Positional and energy increase from right to left, from solid to liquid. Okay, let's see. As temperature increases or decreases, which takes precedence? Oh, we're still working on that problem. As temperature increases, the positional randomness dominates. Ah, okay. I see where we're going now. I'll leave that up there. So why are we saying that in a process, as temperature increases, positional randomness dominates? I'm sorry? As temperature increases? Yes. Well, if we're trying to find a balance between energy randomness and positional randomness, or energy entropy versus positional entropy, we're trying to say which one dominates, and it's largely based upon temperature. So at high temperatures, positional randomness is the dominant driving force. Because once you get to a high temperature, an increase in temperature has very little effect. It's like, say I'm a millionaire, I wish. And you would like to, and I'm not your instructor anymore, right? So you don't think of it as bribery, right? We just meet on the street and you want to give me $1. Okay, you give me $1. What impact is that going to have on my budget? 0, right? So if I have a lot of money, or if I'm at high temperature, a change in temperature or a change in the add $1 to my budget is not going to affect the value much, not on a percentage basis. So, yeah, the enthalpy or the entropy?
Like when it comes to what we're just like it could be like there are limit to it, like,
No, theoretically, there's no limit. It's just that when we're calculating the total and we want to combine energy entropy and positional entropy, when you get to high temperatures, actually the positions where things are located is more important than how much energy, whether you add energy or subtract energy. But at low temperature, right, when you get down to low temperature, say I'm like I am now, dirt poor. If you want to give me $1, that'll have a huge impact on my budget. So down at low temperatures, a change in temperature, adding energy to the system, has a much greater impact than change in position. I hope that made sense. Okay, that's black and white what I was trying to say. So at what temperature, this is a more interesting question. At what temperature is there a balance between energy randomness and positional randomness? At equilibrium. And when do you have equilibrium for physical processes? That's at the point where they're changing phase, either melting or vaporizing. Then, and that partially explains why when you change phase from solid to liquid to gas, the temperature, when you have solid and liquid together, temperature stops changing. It stays the same until all the solid's gone. And then the liquid starts heating up some more. And then once you start getting gas, then there's a place in there where the liquid and the gas are there at the same time, boiling point, and the temperature stops changing until all the liquid's gone, and then it starts moving again. So the equilibrium state is at the melting point or the boiling point. And that's where the balance between energy and positional randomness are equal. I'm sorry?
That would have been fun live.
Which one? Phase change? It might be doable. Yeah. I don't know how yet, so it probably, you'll have to take another chemistry course somewhere to get it. Or come back and retake this one when I figure out how to do it. So we're going to look at these possibilities and classify them as spontaneous, non-spontaneous, or you don't know. Okay, let's look at a chemical reaction that is exothermic and more positionally random. If it gives up energy, it's becoming less random, energy-wise, right? This is decreasing. Let's see, let me erase this. For an exothermic reaction, right, the system is giving up energy, so that one is decreasing. And the conditions say more positionally random, so this one's increasing. All right, so is it spontaneous, non-spontaneous, or can't tell? Well, it says both are favorable. More positionally random and exothermic. I don't get it. Do you? At one time I did because I created the slide. But it doesn't make any sense to me now. Because if the energy randomness is decreasing.
Oh,
It would have to be the total. But the way it's described there, it says that both driving forces are favorable. Exothermic is favorable. Well, what do we mean by favorable? Well, all you're doing with an exothermic reaction is increasing the entropy of the surroundings. Yeah. If it's less positionally random, then it would be, you can't tell. Because you don't know what the balance is. Endothermic, can't tell that one either. And endothermic with less positionally random is not spontaneous. All right, I'm gonna have to think about that one for a while. Maybe we'll cover something like that in the review. By that time, hopefully I'll have it figured out. A and D are not affected by temperature. A and D are not affected by temperature. Well, that's another question I need to answer. All right, now that's true. Well, one's exo and one's endo. The exothermic is more positionally random and the endo is less positionally random. But it says they're not affected by temperature. So if they're not affected by temperature, that means they have to be at lower temperature. Because, no, at higher temperature. Because effective temperature is less pronounced if the temperature is high. Your guess is good as mine. Let's see what's next. So, if we consider the system and surroundings thing again, and we're going to isolate it, then the sign of the surroundings depends on the direction of the heat flow. If the heat flow is this way, that means entropy is out here is positive, and entropy in here is negative. Okay, as heat leaves the system, randomness in the surroundings increases. The delta H is negative, obviously, because everything's relative to the system. So the change in entropy, enthalpy, is negative, and the surroundings increase their entropy. If heat enters the system, then delta H is positive, right? It goes the other direction. This is going to be negative. If it goes the other direction, of course, that'd be positive. And the magnitude of this value, delta S for the surroundings. Let's remove that. Delta S for the surroundings depends on the temperature change between the two. So the change in temperature, what is that statement? The change in entropy has a greater effect on the surroundings when it starts at a lower entropy than if it starts at a greater entropy. Yeah. If we start at a lower entropy for the surroundings, then on a percentage basis, the increase in entropy is more pronounced. It's like that wealth analogy I used. So what we're actually saying is the change in entropy for the surroundings is proportional to the heat transferred. The change in heat transferred. There's a proportionality there. Now, in order to make it equivalence, we need a proportionality constant of some kind. Oh, and it's inversely proportional to the temperature. So what we were saying was, if the temperature is very high, then the change in entropy is less than if it's very low. What we're getting at is a formula. Oh, and obviously the temperatures have to be in Kelvin. Actually, Lord Kelvin was working on thermodynamics when he came up with this temperature regime. He was working on thermodynamics, and I got a copy of his paper somewhere. And then this is in units of joules. All right, so what does that say about the units for entropy? Units for entropy are joules per K, per degree, for K, not degree. Joules per K, yeah, the units of entropy. So for the exothermic process, let's see if this makes sense. Exothermic process, this delta S for the surroundings should be positive. Yeah, that makes sense. And for endothermic, moving the other direction, delta S should be negative. All right, so the problem now is instead of Q there, we're going to use enthalpy. So the delta S for the surroundings is equal to, I guess we figured that it's not just proportional, but it's equal to, since we chose our units, is the change in entropy, enthalpy, excuse me. But we have to put a proportion that this has to be negative. And the reason for that is this is relative to the surroundings and this is relative to the system. So we got to change the sign, right? If delta H, heat is leaving the system, it's negative. But if heat is leaving the system, the surroundings are becoming more random, right? The entropy is increasing. And if we don't put that negative there, then this looks like the surroundings are negative, which means the entropy is decreasing. So we have to have that negative there to fudge, right? Because of the way we constructed the system and the surroundings in the first place. All right. Delta H, enthalpy, and Q are related, but they are different values. Q is actually a measurement of heat transfer, and we did that last semester with our calorimetry determinations. Delta H is more as a potential for heat movement. And we define enthalpy by that equation, right? This we had pressure, constant pressure times change in volume. But in fact, it's really that change in pressure volume product. So what is delta E equal to? I didn't give that to you yet, did I? Okay, delta E. This is equal to Q plus W. So the heat content of the system plus any work that it does or is done upon it adds up to the internal energy. So delta E equals Q plus W. If we substitute Q plus W into this equation here, right, then we get Q plus W plus delta PV. That's equal to enthalpy. If the process takes place at constant pressure, then we can move. Let's see. Let me put, where are we so far? we're at delta H equals Q plus W plus delta PV. And if we hold the pressure constant, then now pressure comes out here, it doesn't change, and volume is the only thing that changes. So W, well, I should have derived this one before. If W equals minus P times delta V, I thought I had that one. No, I didn't. Or did I do that? Did I do that in the previous discussion? I don't remember if I did. Maybe it's in a different slide set. But W equals minus P times delta V. Minus P times delta V. The reason for that negative is similar to this other negative. Because if we calculate work as an increase in pressure, an increase in volume under constant pressure, then that means the system is doing work on its surroundings and it's negative. Right? But if this is negative, work can't be negative because work has to be live by the same convention. Right? If the system is doing work on the surroundings by expanding gas, right, and it goes from a small volume to a large volume, that's an increase, that's a positive value, then we get work being done on the system, and it's not. It's being done on the surroundings. So we have to put the negative in there to change the negative to work on the surroundings. Right. So we need this one. That's equal to W. That one. We're going to work on this one in a minute. We need this one. And remember that one. We need this one equals delta E. Now, if P is constant, let's see. Okay, work, here we go. Work is equal to minus P times delta V. So this one is minus P times delta V plus P delta V Q, excuse me. It's a Q, delta H. So the whole point of this was to show you that they're different values, but they're equal under some special condition where the pressure is constant. If the pressure is constant in a changing system, then that one cancels that one, and enthalpy and heat are equal. So that's why most chemists, when they conduct calorimetric or thermodynamic experiments, they try to do it at constant pressure. That way, when they measure heat, they're actually measuring enthalpy. All right. So let's see. I'll tell you what, let me put the ones we want to remember over here in the corner. Got that one. I think we need that one. We'll do this one. Delta E equals Q plus W. Okay. And work. W equals negative P delta V. Okay. I'll leave that there for now. I need to erase it later. Okay, for this example, when we're comparing, let's see, another one that we're interested in is delta S for the, well, they say universe there. I'm going to say total equals delta S for the system plus delta S for the surroundings. So as a reminder, if the total is positive, we have a spontaneous reaction or process. So if the system and the surroundings are both positive, that's a no-brainer, right? That's obviously a spontaneous process. If they're both negative, then this is negative and it's not spontaneous in the forward direction. It is in the opposite direction. If this one is positive and this one's negative, it depends. It could be positive or negative. Depends on which one's bigger. And likewise, if this one's negative and that one's positive, it could be either way. Okay, now we're going to get into practical application. And there are a lot of different expressions for what we're now going to term as free energy. And chemists and physicists who work with this all the time just love to chop things into small pieces and make the whole thing confusing. I'm on a chat group and it's administered through Reddit. And I get all these chemists coming in and they say, look at what I did. You know, lots of times they'll bring in a picture of a titration, say, look at that pink color is just barely there. I hit it right on the nose. Or they'll, the conversation will drift toward this stuff. You know, I saw one recently that talked about thermodynamics. And they brought up this free energy equation and that free energy equation and this one. There were like a half a dozen of them. So we're going to focus on just this one. It was proposed by Josiah Gibbs. And the idea is that free energy, as the understanding of free energy is how much of the energy that is produced from a chemical reaction is actually available to do useful work. Right? That's very important, especially if you want to make money, because all the other energy is wasted. We want to know how much of that free energy is available to do useful work. And he came up with this equation. That value, the Gibbs free energy, and of course, it's in terms of energy, it's joules. You start with the enthalpy, and then you lose some energy to a change in entropy. So the change in entropy times temperature subtracted from enthalpy gives you your free energy. What is available to do work? So we're going to transform a little bit. Let's divide the whole thing through by temperature, right? If we do the whole thing divided by temperature, that next equation is what you get. Right there. Oh, I see what they did. They made this positive, negative, negative. So we're dividing through by a negative t. Okay, the reason we did that is so that we've got delta S surroundings. And this is going to be delta S for the system. If there are no subscripts, we assume it's for the system. So there you have the surroundings plus the system yields Gibbs free energy divided by temperature. Let's see, is that part of it? Yeah, there we go. And this is equal to total, right? This one plus this one is total, delta S total. Right, so we already know that if this one is positive, the reaction is spontaneous. So what about this one? If this whole thing is positive, then we also have a spontaneous reaction. So if negative delta G over T, if that whole thing is positive, then we have a spontaneous process. So what does that say about delta G? Because T is Kelvin. It's always positive. All right, so delta G would have to be negative, wouldn't it? So a negative delta G means spontaneous. Maybe that's part of the slide. Yeah. Let's see. So we're saying that the process is spontaneous in the direction that free energy decreases because it's negative. All right. Am I making any progress? Okay, what are we about halfway through? Oh, we got Professor Dave's going to talk in a couple of slides. A liquid is vaporized at its boiling point, constant pressure. What are the signs of W and so forth? Okay, so a liquid is vaporized. It goes from liquid to gas at its boiling point. That means we have equilibrium. So the gas will do work on its surroundings. As it expands, it's changing its volume, increasing its volume. It's doing work on its surroundings. All right, so that means the system value is negative. Heat is being transferred into the system. So the value for Q then is positive. Delta S, delta H. Well, Q equals delta H at constant pressure, so that one would also be positive. How about the delta S for the system? What's the system? Well, the system is the boiling water. The gas is more disordered than liquid, so we have a positive system entropy. Surroundings. Heat enters the system. Surroundings become more ordered because we're extracting heat from the surroundings. That means the surroundings are negative. At the boiling point, the system is at equilibrium. So delta G is equal to 0. Any equilibrium situation will give you delta G 0. So if delta H, yeah, where is it? Delta H equals T delta S. Thought I had that one. Ah, okay. It's rearranging this one. But now we're talking about system. Right? If we rearrange this one, then what we're going to get is T times delta S surroundings equals negative delta H. So if the heat is moving one direction with this negative, it's moving the other direction as positive. So now we have T delta S for the system. It's just change the sign. Oh, and I also see it's derived from this equation right here. No, this one right here. Why? Because if that's equal to 0, then delta H equals T delta S. There you go. So either way, the logic works. This is kind of boring, isn't it?
It's just freezing in here.
Is it freezing?
I don't know.
No?
It's not them.
Yeah, maybe you're getting sick. Well, yeah, a lot of it is. Right. Some algebra. Okay. The value of enthalpy of vaporization of a substance is 45.7 kilojoules per mole, and its normal boiling point is 72.5 degrees C. Okay, that's given. We want to calculate the delta S system, surroundings, and delta G for the vaporization of 1 mole of this substance at 72.5 degrees in 1 atmosphere. All right, so at the boiling point, you're at equilibrium. Delta G is equal to 0. That's anytime you're at the boiling point, you're at the melting point, you're at any phase change, delta G is 0. The delta S for the surroundings is a change in enthalpy, which is 45.7, negative 45.7 divided by the Kelvin temperature. So the delta S surroundings is minus 132 joules per K mole. And system at equilibrium, if system plus surrounding entropy is equal to 0, which it is, then you just change the sign. So the delta S for the system is positive 132. So at equilibrium, you don't have an imbalance. There's a balance between the system and surroundings in terms of their entropy. Okay, here comes Professor Dave.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around, entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T, so entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand, because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the nonpolar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water-soluble due to the polar heads facing out. That's how soap works. And that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy-storing processes. In this way, systems can defy entropy on the small scale, But the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, sure. Okay, so if we use this equation here, the Gibbs free energy equation, and we want to know if a process is spontaneous, we need to end up with a negative value for this one. So that means if we know that the delta S is positive, and we know that the delta H is negative, and this is negative times positive is negative. Negative and negative means negative. This is definitely spontaneous. At any temperature, doesn't matter. Okay? All right, suppose we have a positive and a positive here. Well, that means this one's negative and that one's positive. So only when this one is large enough to make it very negative will this one be negative. And that happens at high temperature. Let's see, go the other direction, negative and negative. Here we go, negative, negative. All right. That would be negative here and positive here. So we want to minimize this term. That means T must be low temperature. It's only negative when the temperature is very low. And then we got negative here and positive there. So if this is positive, let's see. Negative, positive. Oh, hold on a second. Positive. I put these backwards, didn't I? No. Positive delta. Oh, those are backwards. I had it right. So this would be positive and negative. There we go. Under these conditions, this one is always positive and that one's always positive. Right? So that one is never spontaneous in the forward direction, no matter what the temperature is. Okay. Let's see, we got a gas A2, which is apparently a diatomic gas, reacts with gas B2 to form AB at constant temperature and pressure. The bond energy of AB is much greater than that of either reactant. Okay, so if we say that one plus that one yields this one, right? To balance it, we need a 2 there. And we're saying that the bond energy of this one is much greater than either of those. So energy is being stored in this side right here. So the delta E over here is increased. What are the signs of delta H, delta S surroundings, system, and total? It says, okay, I put this warning down there. The problem says that AB bond is stronger than A. This bond is stronger than these two. So this bond to there, this bond to there, compared to this bond to there. This bond is stronger than that one, and it's also stronger than that one. More energy is required to break this bond than to break either of those. So that means more energy must be supplied to break AB bond, and it is a lower energy state than either A or B. So that's wrong. The total energy of this system is down because this is a more stable bond. Okay, next slide. If we go back and look at how we calculate the enthalpy based upon bond energies. Right, remember, we can add up the bonds that are broken in the reactants, and then the bonds that are formed, we subtract in the products, and we get a change in entropy, enthalpy, excuse me. Okay, so if the energy of the reactants is greater than the energy of the product, which is that is what we have said, this is an exothermic process. So we got heat given off there. It's more stable. Products are more stable. That means delta H is negative. Okay. How about the orderliness? Okay. If we know that delta H is negative and we put it into this equation, right? Here, put it into that equation. Let's see, let's erase that one, it's in the way. And if this is negative, the whole term is positive. So surroundings, you get an increase in entropy in the surroundings. The system then would decrease in entropy. Well, we can't tell for sure, apparently. Could be zero. We don't know. So the total should be positive. And that means the process is spontaneous. So this exothermic process is spontaneous. That's probably why in that earlier slide they said that and the exothermic, the energy part, the exothermic part is favorable, spontaneous. Right. Professor Dave mentioned the third law of thermodynamics. I mean, it's interesting, but it's not earth-shaking. We just are, by definition, I think, saying that any substance at absolute zero in a perfect crystalline form has an entropy of zero. Now, there have been standard entropy values calculated for just about everything, right? And you can look them up. If we want to know the standard entropy for a reaction, we just need to take the total of the entropy values for the products and subtract the reactants. It's like enthalpy in that way. All right, generally speaking, as the complexity of the molecule increases, its standard entropy also increases. So one illustration of that is water. Right? Water is a very simple molecule. It has oxygen and two hydrogens. What type of movements can it undergo? And that leads to different microstates. So you can have the bond stretches can be synchronous, right, between oxygen and hydrogen. You can have the hydrogens can flap back and forth, right? They can change the bond angle like that, or they can be out of sync, right? They can go like this, or the whole thing can rotate. Okay. But diatomic hydrogen has only two ways. It can stretch one way or it can rotate in other ways, right? So it has fewer options. That means the more complex molecule is water and the lesser complex is hydrogen. The water has more standard entropy than dihydrogen does. Okay, so if we calculate it for this situation, notice that when we were calculating enthalpy for a reaction, standard state elements were enthalpy of 0. But in this case, entropy is measured against absolute entropy, which is 0 at 0K. So every substance, element, compound, whatever, they all have standard entropy values, joules per K mole. So sodium is 51, water is 70, sodium hydroxide is 50, and hydrogen is 131. And if we put them into the equation, and remember, if there's a coefficient in front of, say, sodium hydroxide, you multiply 50 times 2. And we end up with a negative standard entropy for this equation is negative 11 joule per K. All right. So we're starting here with the Gibbs equation. And if we use standard values, the standard free energy is equal to the standard enthalpy minus T times the standard entropy. And delta G is also equal to the delta G of the products minus the delta G of the reactants. Where are we going with this? A stable diatomic molecule spontaneously forms from its atoms. Okay, so what we're saying is this diatomic molecule spontaneously forms from its atoms. So we have two atoms here. And we're going to say that it has to be gas. I'm going to say it has to be gas. Predict the signs of standard entropy, standard enthalpy, and Gibbs free energy. Right? They're all negative, is what they're saying. Right? So if we have these two, what happens when they come together? Right? They give off energy. Right? It's an exothermic process. That's why delta H is negative. Let's see, we have a better explanation than that? Yeah, we do. So delta H, because the molecule is at lower energy than separate atoms, this gives off energy. Or we could put delta H over here as a term. It's exothermic. And delta S, what's happening to the possible microstates? We have more here than you do here. So that means this is negative also. Right? How about delta G? Well, that makes this term positive and that one negative. So I think it has to be, well, at standard, under standard conditions is low temperature. All right, so if this is low here, that makes this small, this large. So that's why we're saying delta G is negative. Okay, how about this one? Let's see if we're getting close to the end. Sort of. Okay. So how about this system? Let's do that. And we have PCl3 gas. yields, oops, forgot the chlorine, plus chlorine gas yields PCl5, yep, PCl5 gas. I need a new marker. And the delta G is given as minus 92.5, minus 92.50 kilojoules. Okay, what will happen to the ratio of partial pressures PCl5 to PCl3 if the temperature is raised? Well, if it's spontaneous, going this way, that means this is negative. Right, that's negative. This is more ordered than that because you've got a mole here and a mole there, and you only got one mole here. So the delta S should also be negative. What about delta H? I had to keep in mind the question. What's the ratio between PCl5 and PCl3? So we're looking for what happens to this ratio, PCl5 gas versus PCl3 gas. So what are we saying? Is it spontaneous? Will it move this way and increase that value? Right? Or does it prefer this side and decrease that value? If the ratio decreases, that means this side is favored. Right? So the spontaneous is not spontaneous in this direction. It's spontaneous in that direction. This is small, that's large. Now, how did they get there? Okay. Delta S is negative. Yep, we got that one already. But the reaction is spontaneous. Oh, if it's spontaneous, then it wants to go that way. Delta H must be negative, exothermic. If that's true, if that's negative, this is negative, then this has to be negative and large enough to counterbalance that one. So it is exothermic. So if it's exothermic now, we can put the term over here like that. Okay, that's where we're going. Did you follow me so far? Right. Delta G, it says it's spontaneous, so that's negative. And then we know that we're going from 2 moles here to 1 mole there. It's the entropy is decreasing from left to right. So if this is spontaneous and this term is positive, then this one has to be negative, big negative. And that means exothermic. So in exothermic reaction, we put the heat term on this side. Now what happens when you raise the temperature? When you raise the temperature, adding that term. And Le Chatelier says, it's going that way. That means you're going to have more of this and less of that. So that means this value is decreasing as temperature increases. Well, I had to go around the barn 3 times to get that one done. Yeah, there we go. All right. So how does actual free energy, how do we calculate the actual free energy of the reaction under the conditions given compared to by using the standard free energies and other factors? Well, it depends. It depends on whether your system is in terms of molarity or partial pressure. So, well, actually, either one of these works. If you want to find out the actual delta G, and say these are the standard conditions. If you want to find out the actual delta G, which is what we're really after, because this only works if the conditions are standard. This is under current conditions. So we start from here, and then we add any changes in temperature and pressure. Or we can say it like this. Right? Our equilibrium expression will give us Q. And in this case, since these are all energy terms, we have to use the R value that has energy in it, 8.3145 joules per k mole. Okay, what does delta G mean for a chemical reaction? What we're looking for is the lowest possible energy state. Not necessarily going to completion, but finding the most stable energy position. In a phase change, this example on the left, the phase change, the only stable position is completion, going all the way down to the end of the ramp. For most chemical reactions, there's an intermediate stage here, right? We don't go all the way to B, we stop at C, because that's the most stable energy situation. And that relates, I think, to equilibrium. Because once you reach that position, then you still have some reactant and some product. And their rates are equal, forwards and reverse. But this still happens. The equilibrium point occurs at the lowest value of free energy available to the system. And if delta G equals delta G 0 plus RT log what? Well, in this case, if delta G 0, if we're stable, then there's no impetus to go either way. Then this delta G equals 0. That means delta G under standard conditions plus RT log, not Q anymore because we're at equilibrium. So what goes in here instead of Q? K. So 0 equals delta G 0 plus RT log K. That's a very useful equation too. Put that one over here. Well, let's solve it for, if that's 0, then delta G 0 equals negative RT log K. And this is for equilibrium. Okay. This slide is a little hard to follow, I think. So if I mess it up, you see it coming. So what's the change in free energy to reach equilibrium? Well, let's see. In a process of going from A to B as a gas, we have free energy of each gas expressed as, well, I erased the term. Oh, no, I erased the term. Let me put it back up here. If it's a gas, then we got a pressure of each one. So the free energy of this one is the free energy, standard free energy, plus RT log partial pressure of A. All right, so we can calculate this value if we know the standard and we know the temperature and we know the partial pressure. And B likewise. Those are how we calculate each one. So the total free energy is simply going to be whatever A happens to be plus whatever B happens to be. That's simple enough. Right? As A disappears, right, where is that happening? The fraction of A, the first plate there, fraction of A reacted. Right, so the actual G is decreasing because we're using up A, going to the right. The free energy of A decreases since the pressure is decreasing, right? We're using up A, pressure is decreasing, so G is decreasing from left to right. Okay, so far so good. As B appears, okay, so we're going from A to B. That was the reaction. We're going from gas A to gas, well, let's see, that's an equilibrium. So we're doing this thing to gas B. There we go. So as the reaction proceeds, we're getting more B. And if we look at what happens to B, we get an increase. We get an increase in pressure as B develops. So now this one, as this decreases, that decreases. And as this increases, that increases. So as long as this one is less than that one, then we get a movement. It'll proceed to the right. When they're equal, when these values are equal, then we have a stable value for the total free energy. And if we look at it in terms of reactants and products, the delta G for the whole reaction, delta G equals the whatever the G for A is plus the GB. Excuse me. This will be B minus A, right? Free energy of B minus A will give us the total. So if they're equal, then the delta G is 0. And that's when we're at equilibrium at whatever, and it changes for the type of reaction. This is just a hypothetical, right? And you find yourself at the bottom of that trough, minimizing the delta G. Actually, the delta G drops to 0. All right, let's look at something a little more useful. Right, when we have this equation right here, delta G0 equals minus RT log K, and that's at equilibrium. If, yeah, at equilibrium, the actual delta G is 0, but the delta G0, if it happens to be 0, if this is 0, right, what does that mean for this K? Well, what if this is 1? If K is 1 and this is E, right? E to what power equals 1? No idea. 0.
0, I do know
Yeah.
that. Anything.
Yeah. Yeah, anything to the 0 power. So this term becomes 0. And that means the whole thing is 0. So if K equals 1, then delta G0, the standard condition delta G is 0. If K is greater than 1, right, that means we have to have a positive power of E. And a positive power of E gives you a positive value here. So K is greater than 1. and vice versa. Right? If K is less than 1, then we get a, if K is less than 1, then we get a negative value for this term times, excuse me. Now we still get a small positive value here. And that makes the delta, no. Negative times negative is positive. All right, so if K is greater than 1, then this is going to be negative. Yeah. And if K is greater than 1, this is going to be positive. So the reaction is spontaneous at standard conditions if the K is much greater than 1. And it's not spontaneous if it's less than 1. All right. Almost done, yep. Okay. The maximum amount of work that you can get from any process at constant temperature and pressure, of course, is equal to the change in free energy. So that's where this other equation comes in. The maximum work that's available, according to that equation, is equal to the true delta G for the reaction. So if the conditions change, then the delta G might change, and that will change the amount of work that you can get out of it. What we've learned also over the decades is that all real processes are not reversible. Right? They're only reversible theoretically. If you make a very, very small change in volume, very small, infinitesimally small. In calculus, we call that the limit of small. Then a reversible process would be able to extract all of this free energy in useful work. But since processes are not reversible, they're irreversible, then the maximum work can never be reached at that point. It's always less than that. All right, what we're saying in this slide is that the K is dependent upon temperature, and we know that from previous discussions of equilibrium. But equilibrium also occurs at the lowest value of free energy available to the system. So the lowest actual value here will give you the lowest amount of free energy in equilibrium. So what we're saying is that delta G equals 0, and then that, let's see, let's go ahead and put this up here. At equilibrium, that's true. And that's also equal to this standard plus RT log K. We know that. And we know that in that case, we get this equation right here. I guess I better put it over here for consistency. Negative RT log K. Okay. So in this case, delta G0 is equal to that, but it's also equal to this right here. So this is delta H0 minus T delta S0 is equal to this term, right? If A equals B and B equals C, then A equals C. Then if we divide the whole equation through by minus RT, what do we get? Well, we get minus delta H0 over RT, and then minus in a minus means a plus, and T's cancel, so we have delta S0 over R, and that's equal to, minus RT cancels out, that's equal to log K. Okay? Well, if we flip that around, right, we flip this around and put log K over here, and then we put delta H0 over R, and we factor out the temperature as an inverse, and we still have delta S0 over R. Now what we got is something that looks like a straight line, right? Y equals mx plus b. What that means is if you have a series of reactions and you measure the K under conditions of different temperature, and you plot, let's do it over here. If we plot log K as the Y and 1 over T as the X, then the line is going to have a negative slope. And the slope is going to be negative delta H over R. That's equal to the slope. And the y-intercept right here is going to be delta S0 over R. So if we plot this out, R is a constant. And since R is a constant, if we know the slope value, then we can calculate the enthalpy, standard enthalpy for the reaction, and we can calculate the standard entropy for the reaction also from that plot. And that's what this looks like. So when you see that data plotted and you look at the equation, y equals minus 11,645 x plus 24.924, 24.924 is equal to that. Right? And this one, slope equals negative 11,645. Right? So take away the negative, and this positive value is equal to that. We just divide it by, multiply it by R, and we get delta H. I think there's a name for that equation, but I can't remember what it is right now. Okay, this is just a restatement of something I said earlier. Maximum work can only be obtained from a spontaneous process that occurs in a reversible situation. Go backwards or forwards. But since all processes are irreversible, then the real amount of energy depends on the path that you take. All right, so here's a prose definition of the 3 laws of thermodynamics. Remember, the first law says that the total amount of energy change in the universe is 0. So the first law says you can't win. You can only break even. Can't get more energy out of a system than you put in. Okay. Second law says you can't break even. Any transfer of energy will result in a waste of energy unless a temperature of absolute 0 can be achieved. That'll never happen. Right? So the first one says that you can break even. The second one says you can't even break even. And the third law says you can't even get out of the game because you can't achieve an absolute 0. Never, ever. And entropy produced. Uh-oh, that happened. Guess it's as good as mine. All right, that's it. That's enough. Next week, we'll look at Let's see, let me mark this off. We did that today, we did that today. Next week we'll do. Oh, you won't be here, right? Okay.
Review will be on Brightspace.
Oh, yeah. Yeah, I'll record it.
And then the chapter 6 test will be on Brightspace.
Yes.
Do we have a class that day? Yeah.
Yes,
Because you have to do,
we're gonna do the review. Right. You need to view, take the exam on Brightspace for this material. And then when we come to class, we'll do a review of chapter 18 that you've already viewed. Okay.
is that, I know before there was problems with the lockdown browser. Have you already fixed, like, yeah, I didn't take it off. Did you take off?
I'm not sure. I'll do that before I leave.
I know it didn't work.
Yeah. So let me check it, see. I may have already done it, but I can't remember. So that's recording. We want to, come on. End. Come on. End the meeting.